All right, we're here. This time, I'm pretty sure we're live. So, um, mic levels looking good. All right, chat, you'll have to let me know if you can hear me or not. If I need to adjust anything. You just tell me, and I will adjust. Welcome back to another week of happy, awesome, cool, chill, relaxing Haskell hacking action. We've been working on making an asteroids clone in Haskell. And if this is your first time tuning in, this is what our project looks like so far. Just going to run asteroids. All right, last week I was working on hitboxes and collision detection. And so you see there the asteroid got depleted by impact with the bullet there. So that's what we've been doing is that. So we're going to continue down that road with handling those collision events. What should happen other than just removing the asteroid? We also have to increase the score and things like that. Spawn in new asteroids, all sorts of stuff. Pow, pow, pow. So there you go. Asteroids. So look at my project here. Let's open up. Pow, pow. Oh, some unstage changes. Just some white space. Let's kill that. Okay. Asteroids. Game. Okay, so to review, there were some technical difficulties with the stream last week. I'm pretty sure I sat here and talked to nobody for a couple hours, which was super fun. So yeah, I'll just kind of quickly review what we did. So of course we did a lot of refactoring with the player ship and the physics and all that stuff, but for collision detection, right, we added this collision box record type. I added a collision box as a position and a size, and we have a function that can check if two boxes are colliding. And we have this class, has collision box, so that a type that can do collision will implement an instance of this class here. And the idea is that that type will return the collision box. And so we implement that for bullet, right, where it returns a new collision box based on the bullet's current position, the width, and the size of the bullet, and what it should collide as. And the asteroid, as you saw, we were actually rendering the collision box there, so we can test, its size and if it's the right size for our game, for our asteroid that we made. And that's built off of the asteroid's position. So we kind of tweaked the width and height values there. We offset the box because the asteroid's position in the middle of the thing, and the polygon is kind of surrounding that point. So we offset the top left corner of the box based on that. So then when we render the asteroid, we also render the collision box there just for testing purposes. So the thing we do when we get a collision, we detect it, is we handle most of this stuff fairly manually, actually. You'll see in a lot of game engines some kind of collision system that will often implement some form of like a publish subscribe kind of message-based system. We haven't really implemented anything like that because we're not being super fancy here. This is just asteroids, so we just kind of implemented the first thing that we could make work to get us one step closer to a finished looking game. If we find a need for a system like that, we might implement that. But I guess the idea with projects like this is just to like keep it, just write the code. Don't write an engine. You know, just write the code. So I got a few tests, I think, for moving on the pseudorandom stuff. Or I commented that out for now because it was kind of broken. I will reintroduce that later, but some collision box tests and stuff like that. So that's what we did. This week, we are going to improve upon this a little bit and add more collision detection goodness so we can increase the score, spawn in more asteroids, so on and so forth. I'm kind of curious what our asteroid spawning action should be and how the original asteroids spawned in new asteroids. Kind of curious, actually. Maybe we should look that up. How? Mm-hmm. No, Space Engineers is not the game we're looking for. This is somebody else's version of asteroids. That's not quite it. I don't know. Original asteroids. Let's try it. Original asteroid spawn algorithm. Game logic, maybe. Oh wow, this is building the original analog version. Or digitalish. Oh wow. Building a whole computer just to play asteroids. That's cool. Okay. Well, we'll just make something up. Something reasonable. That seems fun. No worries. Okay, so I guess the next thing let's go to the collision code. Check asteroid collisions. Okay, so we kind of want we return this updated list, these updated decks or lists of bullets and asteroids because we filter them out, and the algorithm for it is a little bit meh, but it's should be commented a little bit maybe. I'll go ahead and do that now just quickly. So the idea with this recursive algorithm here, this Go algorithm, is just a helper function for filtering out like marking and sweeping through the bullets and the asteroids at the same time and kind of marking which ones need to have their dead flag set. Recursion is the input bullet or final state of the input bullet list of asteroids that may have dead flags set. Right, and the idea is that as we go through, we recur on the list of asteroids, and as we go through with this bullet, this bullet that's input is going to be the one that's modified as the final output. So as we go through, if there's no more asteroids to check, then we just return that bullet because there's nothing else to compare it to. Otherwise, we have at least one asteroid to check the bullet against. We check if it's colliding with that, and if it is, then we recur and we set the state of the bullet's flag to is dead equal true. We mark that asteroid is dead as true and accumulate with accumulated asteroids. And we recur. Otherwise, we just recur with the bullet as it is so far, the asteroid, and so on and so forth. So that's just how we're sweeping through and marking them as dead. But there's a couple other things we want to be able to do to the state as well when a bullet is, or an asteroid is destroyed. We want to increase the score. So we need to come up with a good pattern for manipulating the state. Because if we pass in the game state and then check asteroid collisions, has to like get a copy, the whole copy of the game state, and change all these things, and it can be quite complicated moving all that stuff around and making sure it gets put back in the right places and blah, 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 blah. So what I'm thinking we should do here is return some kind of result object. Oops, that's not what I want. Return some kind of result object that tells us the state manipulations that should be done. Or, in this case, also maybe includes some of the data that needs to go into the state. And then the state function can do this actions check collisions function and take that result and interpret it and change the state accordingly. And that way we localize the state transformation that we need to do in one place. So this function could just say like, hey, do this thing as the result. So I think we'll try that approach. Because the next thing we need to do is we need to do ship stuff. And like the asteroid collisions can do a bunch of things, right? It could spawn new asteroids, and you know, if it's a large asteroid, it's going to do something different than if it's a small asteroid, and that sort of stuff. So yeah, we should do a collision result type. Right, so these are the different collision results that can happen. We have bullet collided with asteroid. That's one case. We could have, let's just focus on that one for now. I know this is going to want me to make this a new type. No, it's not, because it's going to be data because it doesn't have any constructors yet. But anyways, I'm getting ahead of myself. I'm anticipating which GHC is going to tell me. So collision result. A bullet collided with asteroid. All right, which bullet, which asteroid? We could even make this encapsulate this tuple here. Or what else can we do? I'm thinking, yeah, I'm thinking maybe we should just do bullet here and asteroid. Yeah, because if we do it this way, right, then we have the bullet collided with asteroid, and we can move. Let's let us extract this part out and like how to mark all the flags and stuff. We just have to check if they're colliding or not. And then interpreting a bullet collided with asteroid event not only can do this stuff, but it can also do the other bits. It can even check these arguments and dispatch to a subfunction to update the state in the appropriate way. So like for large asteroids, it could do one thing. For small asteroids, it could do another, that sort of stuff. I think that was pretty good. So let's make this. Actually, let's start our builder here. And then we'll do that. We'll start that refactor there. So we still need this filtering logic, so I don't want to get rid of that code. Oops. Accidentally deleted a character while I was doing stuff there. Okay, so check collisions. We will refactor out that. It'll return a collision result. Actually, I'm just starting a new function here to make this a little easier. So you give me the asteroids to check, the bullets, and I'll return a collision result. And yeah, we'll do the same logic here. Actually, maybe I didn't have to do a second function. Handle bullet collision. At least our state will be a little bit different, our initial state. For this fold, we don't really need to do a fold and collect any state here. We just need to check. And actually, this will be more than one collision result, potentially. We could check all of the bullets and asteroids in one go. So this could be at 0 or more collision results collected together. Yeah, that seems right. In which case, this wouldn't be a fold necessarily. Although it could be expressed that way with an empty list of our collision results. And handle bullet collision. Let's get the type of that. Near. Formatting, fun times. Yeah. So then we still have to do something with asteroids here. So we're kind of going to go with the same recursion, I think. Yeah. Empty list of collision results. and the bullet. And we'll transform the asteroids into a list as we did before in the other function. Except Go now will collect a list of collision results instead of the state from before. It'll take a bullet, a list of asteroid, and return a list of collision results. So that's what we'll build up. No, it doesn't need to do that. It can just be this, I think. All right, there's nothing to compare against, so just return the empty list. But if we have a B, an A, and some more A's, then we can is colliding. A with B. And if that's true, then we collect our collision bullet collided with asteroid results. Of the B and the A. Const onto the natural recursion of Go. B with the rest A's. Otherwise, we skip this one. There's nothing to do. We recur with B on A's. So is colliding is just the same as before. So almost the same, actually, it ended up being. Sorry, not A's, asteroids. We can get rid of this. And then we need to pull bullet into scope. So we don't need the fold. No, maybe, oh yeah, this is for, so Go checks one bullet against the asteroid list. Yeah, so I think we do need the collision results accumulated. Yeah. The results, like, so far for each bullet. So then we have to do something with collisions, and so we will extend collisions with natural recursion of Go. Okay. Okay, so that compiles. So now we have the list of collision results for this check. And now we can do our interpretation of this result. So where we use check asteroid collisions is here. right? We want to replace that. How are we going to handle this? Well, let's use our new function. This returns not a new deck of A's and B's, or bullets and asteroids yet. All right, just a list of collisions. And then we have the filter dead bullets, filter dead asteroids business. So what we should do here... to filter the bullets and asteroids. We still need the B's. We can get the B's and A's, rescue the B's and A's that we had before, maybe, using our interpretation. So maybe we write a function like handle collisions. And that'll take game state, actually. So instead of A's and B's, we might actually just return some, let's call it state prime for now. This could be a little... Well, we might want to refactor more stuff into this pattern, actually. Because we've had trouble with our state update logic being laid out like this before, because different things depend on prior things, which is what ends up happening in this sort of pattern, where you have lots of stuff like this. So it can be tricky to know when to update stuff. Remaining bullets, remaining asteroids will depend only on A's and B's that are computed, and they get put game state ticks, player ship, bullet timer, bullets, remaining bullets, asteroids. So they get updated directly in this state. Don't depend on any prior let bound things that are computed, other than making sure that the original checks the updated positions of those objects, this frame. So I think we can hand state as is into collisions. Although it might be tempting for handle collisions to use the game state bullets, game state asteroids in there. Because it has free access to everything in the game state, right? But it needs it. That's for sure. I don't know. Let's try it out and see what happens. So if we do it like this, we pass in the state and the collisions. This will become state prime. Let's imagine we can get rid of this. We'll just comment it out for now. Okay, so we need this function in scope. We don't have it yet. Let's just grab it from our type error here. It's going to return a new game state. All right, handle collisions. We're going to fold over each collision results. Our initial state for this fold will be the game state we're given. And our input will be the list of collision results. And the final value we're going to be computing is a game state. Okay. Let's handle each result one at a time. Handle collision results. This is we'll just call it GS here, and so the only one we need to handle right now is bullet collided with asteroid. Let's pull out our bullet and our asteroid. Okay. So here we have to return a new game state. And, well, the only thing we really need to do, we know the collision has happened, so we don't have to go detect it. We just need that filtering function, right? To mark the ones that are dead that should be dead, and then to filter them out and update the game state. So basically this logic here. Let B's and A's, bullets and asteroids. I'll handle, we'll call it something else. Mark bullets, mark dead bullets and asteroids. And this means we're going to get 2 sweeps over, actually, our state here. And the whole nice thing about check asteroids before was that it did it in 1. Yeah, I'm not liking this so far. I think the collision result thing is still good. But I think we should return the bullets and the asteroids there in that event. And just pass that back up with this constructor, which will allow us to do other, like interpret that result and do the other state updates that we need to do. Because I'm not liking this idea of just returning the detected one as a list, and then doing another sweep through to mark them dead and alive. Well, the other thing that we could do is that when we get this event, we could all set those so that they already have their appropriate flag set in this event. But then we need to replace those in the decks and, like, yeah, extra work that we shouldn't be doing. So let's not do it. I'm going to go back to my Magenta. Yeah, save it. We'll just get rid of... Oh, it's all tied up and everything, isn't it? We'll get rid of that hunk. And that hunk. We'll leave the comment that we added, because that's nice. Okay. So let's do that. Collision results. Bullet and asteroid collisions. On deck bullet. And the deck of asteroid. It's going to want this to be a new type. Okay. So this is going to return a collision result. And in order to make that compile again, we're just going to wrap this in the bullet and asteroid collisions constructor. Okay. So then in order to fix this type error, we just have to, we can put our constructor name on this side here. I mean, it's not cleanish code, but we know that's the only constructor that's going to be used. Okay. So that at least keeps it compiling. That's nice. Now, the other part. So let's add a score. So when you blow up the asteroid, it changes the score. Well, let's get rid of this warning. Okay. Game state score. All right. The next thing we need to do is add an initial scoring to start up the game. Game state score equals 0. Equals to 0. Just like that. Okay, now now we can do like an interpreter like we were trying to before. All right, so instead of that, we go like this. We make this collisions. And like that. Game state, list of collisions, or collision results. Right. Okay. So now that we handle the collision results this way, we don't have to do any filtering or checking anymore for that. We do it in one sweep. Again, because we're not using a super efficient algorithm here for collision detection, but we don't really need to because we're limiting the number of entities that are going to be interacting. It's fairly constrained, and we're quite comfortable with brute forcing these checks. Right. But in a more complicated game where we have a lot more object interactions that can happen with colliding things, then we probably want something a little more sophisticated than for every bullet check every asteroid, which is basically what we're doing. But again, when you're just when you're making your own games and you're trying to get a project done, don't let the enemy of good enough get in the way, which is perfect, right? I don't know. There's a saying around that, about the enemy of the good is good enough is just write the code that makes the game work, right? You're not doing it wrong by doing it this way. So yeah. Anyways, I don't anticipate us having any frame rate issues with handling collisions this way. Is what I'm getting at. So handling the collision results now. We can have the game state. And we can do our fold prime with handle result, handle collision. And our initial ALV game state. In fact, that's all basically point free. Where handle collision. All right. We're game state into scope here, and we can pattern match out our result now. Bullet and asteroid collisions. This is our updated bullets and asteroids. Right, and all we do right now when we do this is filter them out. So we can return game state. And we can just do this state changing operation down here instead of up there. All right, so game state bullets can be filter dead bullets, these, and game state asteroids, filter dead asteroids, these. Oh, it's not a tuple, sorry. Or is it a tuple? It is a tuple, yeah. Sorry, I just had not the right syntax here. There we go. And that should be A's, of course. Okay. So now, let's get rid of these other type errors. Oh, okay, yes, that's right. So this type error here is because we're returning from our check asteroid collisions, we're only returning one collision. I guess I'm hinting at myself that I'm going to later add more collision types that we can collect together. So for now, I'll just make that a hard-coded list. Then we don't need this or this anymore. We shouldn't need those two lines, and this can be returned as state prime. And if this refactor was successful, then our game logic shouldn't change. It should still be the same. All right, boo, boo, boo. Here we go. We can, and we should be able to shoot that. And it goes bye-bye. Okay. So we kind of isolated a bit of the state update logic into this separate function here. And now we can add the scoring update. Game state score equals game state score of game state plus 1. There we go. And we should be able to see that actually getting updated. So let's just use debugging for now to do that as like a cheap way of seeing that, so we don't have to do all the rendering code for it, and we can do the rendering code in another pass. Import debug.trace, handy dandy friend. We'll do that. It'll spam a lot, but that's fine. Debug.trace, and we'll do it after we calculate the state prime. Yeah. Show game state score state prime. Oh, this might not work because of the record update syntax not silliness. That's annoying. I'll do a little helper function down here, I guess. Okay, so when that compiles and links and everything is good, we should be able to run this game and see that it's kind of spammed to our thing, but it looks like it's updating on every frame. What's going on? That's not right. Why is it doing that? Oh, because we always return. Yes, okay, I know that's happening. Because the collision result is we always return the deck of bullets and asteroids that we wanted to change, but we haven't we're interpreting this as like that a collision has actually occurred, where that might not be the case with this logic. Because it's just the only time we should actually increase the game state score is when we actually have dead bullets and asteroids this frame. So we can return that with our result. If we can we return that with our result? Maybe. Yeah, I think we could. Kind of weird. It's almost like this is doing too much work together, but it is because we want to avoid doing too much work at all. But we're packaging up all of this stuff together, so I think we should be able to put like a did collide flag or something like that. Because the collision result here is, it's only going to be, I don't want to have to like pass through the list again of all the bullets and asteroids to check for deadness. When in handling the collision results and building this up, like we can figure that out and return that. So I'm gonna go ahead and say like maybe we should have a flag in here. collision. Did collide. No collide. It's almost like Boolean. Almost exactly like Boolean. But it's not a Boolean. It's no longer a new type. It's now going to be data. Okay, and so now, in order to return this, we need to return this. Well, this has to check for it. We'll call it like the result. And then the game score can be... Can we use guards layer? I don't know. Case result of did collide. Well, there is no collide. It's just a game state score of game state. Okay. So then updated entities can be this part of it. And this will be collide flag, maybe? And then we have collide flag and update dead entities. Kind of what I want to write. But this fold isn't going to handle that on itself unless we make it a triple. So let's make it A as B's, A's, and collide flag. I think that makes sense, right? And then we can, that is B's and A's, just as before. In fact, we can probably get rid of that tuple entirely. And then we can get rid of the tuple here. Okay. And we can get rid of the tuple here. is no longer a point free function, so we have to bring bullets back into scope and pass it into our fold. And our initialize the state of the fold with no collide at first. Okay. So our handle bullet collision function needs to have this, where it has collision, and then returns a collision. And then CF will be our collide flag. Okay, so when we get down to this branch here, go needs to does the actual check is colliding, so it's got to return that flag as its thing. Slide that here, collide. And for that case, oh sorry, collision. Collision, boom, boom. Okay, now that's the empty case, no problem. Now we have here CF flag. We don't really care about it here, we just care about setting it. Although I think we need to pull out the CF flag if it doesn't change. So I'm going to pull it out. Actually, so it is colliding now. We'll return go and set the bullet B and the asteroid B, and did collide. And then in this case, we only have to pass CF through. It's unchanged, whatever it was. So we only care about the one time. So this basically means if a collision happened, we'll increase the score. Of course, we need to set that up here. We'll just pass that along as the initial state for the recursion. This path. Yes. This needs to get passed back up. Call it C flag. C flag. There. And then it all compiles again. Okay, so now when I run the program, now it should only increment the score when we actually have a collision. So it's there at 0. Boop. To blow up, let's blow it up. Boom, now we got score 1. Cool. So that's that. Okay, let's get rid of the debug. There we go. I'm going to call this collision flag instead of just collide. All right. Allow me to rehydrate. There we go. Cool. So in this change, we add a score to the game state, and we increment the score when a collision with an asteroid happens in a frame. Now this is only checking if a collision happened. If somehow on a frame we manage to destroy multiple asteroids, it's not going to reflect that in our score, which could be problematic. So I'm going to commit this as a work in progress for now, and then maybe we'll try and fix that. Add scoring when asteroid is destroyed. When a bullet collides an asteroid, you put work in progress on this. Destroy the asteroid and bullet and increase the score by 1. Okay, still work in progress because we're not quite done yet. We may want to, instead of just did collide at all, collect all of the collisions. Or just actually calculate the number of collisions that we've detected as we're doing this sweep and return that. So maybe we don't actually need the collision flag, just the number of collisions. Let's see. Let's go down here since we were down here last. So if we change the state here from collision flag to just an int, then CF there makes sense. Let us CF, call it collision count or collision num. Call num. And if we have one, then we will call this call num as well. And instead of did collide, we'll just say call num plus 1. Otherwise, we did not detect a collision for this bullet, so we'll return call num as usual, unchanged. So then a collision flag here needs to be changed to int CF, changed to column, just a column as well. Working our way back up the tree, so we start off with the initial state column. It's no longer collide flag, we'll call and the initial state for it should be 0. Right. And then we'd have to change this to an int. I think this will make more sense, actually. This will be better. Okay, so when we go to handle the collision results now, we don't have to case the results. Not a result anymore. Num collisions. And then we can increment the score. The game state score of the game state plus the number of collisions. So the number of asteroids that were destroyed this frame. Cool. And that should work a bit better. And then, just to test it out, let's add a second test asteroid to our scene and make sure that we can... It's going to be tricky to test, actually. Well, I mean, not terribly tricky, because that's just a pure function, I think. So we could write a test case for it. But I think I'm pretty confident in it, so I don't think that'll be necessary. Okay. C flag, C flag, C flag. This warning here, we should clean that up, of course. Does anything in scope need columns? It needs to be called column. Oh, but then we got name shadowing. Okay. Handle bullet conditions, collisions. Oh, okay. This will be like the next number of column. Be for each bullet. Maybe we should write a test for this. Just to make sure this logic is right. Okay, well, let's just check that the game works still as we expected, as we play it. And then we'll write a quick test case for that just to make sure that we got that right. Okay, so before we get into that, we will commit this. So add the collected number collisions to increment the score. And yeah, we'll just do the test case just to make sure. Cool. Describe. Check asteroid collisions. Do context. When there are multiple collisions detected, should return the number of detected collisions. So here we have to build up a deck of bullets and ships for our example. Or sorry, bullets and asteroids. So we need our EXT, our extension, GHC extensions from list for our bullets, and we'll do the same thing for A's. And once we have those, that would be 2 decks of asteroids and bullets, yeah. So then we should check the asteroid collisions for our A's and B's, and that should be a collision result of bullet and asteroid collisions. We just need a small test case. Let's make it 2. So we'll have 2 bullets colliding with 2 different asteroids, and 1 bullet and 1 asteroid not colliding with anything. And then we'll have to have our expected asteroids, updated asteroids in these. So it is doing a bit of work together, which is making writing this test a little bit tricky, but that's what happens when you bundle up logic together. Sometimes you got to do it for the performance. And so expected these equals something, expected A's something. It'll be we'll figure out how to write this. So this will be expected A's, B's, expected A's. Let's bring that over to the left a little bit. Okay, then we need that import. All. Okay, so I think that should be like that. B's. We'll get our bullet. Our bullet position for this one. Be a V2. Let's say 0.5 and 0.5. Bullet position, a bullet velocity. Doesn't really matter what the velocity is. Just 0, 0 it. Bullet tick doesn't matter either. So we will just make a dummy bullet with most of this stuff filled in, actually. And like that, sure. Bullet tick doesn't really matter. We'll just make it 0. And bullet is dead. False initially. That way I can do this, or I can do B, where bullet position. 0 that out as well. 0.5. Hey, Countorin, welcome to the stream. I am great. How are you? Thanks for joining. Nice to see you. Bullet position, V2 1.5 and 1.5. And a final bullet, V2 like 2020. Doing some advent of code in Haskell. Nice, nice. You doing the 2022 one? Yeah, I'd love to see one. just going to finish writing this test case, and then, yeah, let's take a look. Okay, so B, we have our test B bullet positions here, and now we're going to do the same thing for A asteroid. Sweet. So our asteroid points don't matter a whole lot. So we'll do asteroid points. Is it 6 points? One, two, three, four, five, six. Yeah. Asteroid position is what we want, but we're going to zero that out as well. Asteroid velocity. Rotation. That'll be float. Zero that out. Rotation speed. And asteroid is dead. False. Sweet. Okay, and then that should make writing our expected B's and A's pretty straightforward as well. Okay, we're gonna expect the B in the first position to be bullet is dead. True. Same with the second one. So we wanted to have 2 bullets in this example that have collided. And then oh, we need to set these fields as well to be the same. Okay, well, let's take a quick little break here and check this out. All right, day 7. Day 7. Yeah, I actually haven't finished day 7, I don't think. So this is neat. All right. Yeah. True. Cool. So let me see if I can understand what's happening here. So day 7, as I recall, is where you're trying to, you have a couple of different you have like a directory structure, right? A list of files, and you're trying to find the sizes of things. Yeah. So you read the input, you pass the output of this function into this. Take 2 from reversing this read P to S of P. Okay, so I'm guessing P is the solution. Okay, collect. What's the type of that now? I can't quite remember that. But I'm guessing it's some kind of applicative. Yeah. So we're collecting together. Many and choice. Those are, I recognize those. Hmm. Okay, here's the definition of collect. That's why I don't recognize. Add directory. Hold one. Sum tup. D's. Two tuple. Fold one with addition over F's. So I guess files, F's is like a list of files, and D's is also a list as well of directories. Okay. So it looks like this solution's like running over the parse tree. Is that right? And collecting the results together. Oh, that's all good. Yeah, no, it's fine. All right, so if I think what it's going on here is this is like running over the parse tree of your input and collecting together these numbers as it goes along and summing them up. Right? Was that right? So we CD into many. Yeah, recursively. Yeah. Yeah, exactly. Directory, string directory, get the word. Word. We get a number, a car, space, and then another word, and then a car slash n. Up is a cd dot dot. And number is just a parser that reads the digit. Yeah, so that's neat. That's a neat approach. Very succinct. Mm-hmm. Yeah, I think my first stab at this was probably a little bit clever. I was parsing my input into a data structure that I could use a zipper to recurse over and collect the state as I go along of the sizes. But this is pretty much the same thing, just a lot less code. Because writing zippers can be fairly verbose. And I was trying to use the generic zippers to get rid of some of the boilerplate so I didn't have to write the zippers myself, which sometimes you have to do, but scrap your boilerplate and such. But navigating my data structure with scrap your boilerplate was the part that I was like getting tripped up on, and I just lost motivation for it. So this was actually the day I gave up on, I think, and didn't proceed. But this is neat. This is a neat solution. Very clever. Did you do part two? Let's see. Yeah, cool. Very similar, just I guess different, a different computation. Oh, that's very clever. I like that. Yeah, because like the parsing it forms the tree itself. So like you're basically walking over the data as you parse it, right? That's neat. I don't think I would have come up with that. That's cool. Thanks for sharing. If you can use applicative over monads, it's always better. Yeah, yeah, I think that's a very good point. Touches on something that I've been discussing a fair bit in with other Haskellers lately, um, which is like this whole simple Haskell movement. So if any of you watching don't know what simple Haskell is, maybe because like you're just Haskell curious, you might eventually come across this idea. With simple Haskell, I think the intention is good, and you know, and the intention is good. Haskell has a lot of features, and it's a fairly big language. Some people I've heard call it like the C++ of functional programming languages. Um, I I don't think the comparison is quite fair. um, but the idea is that you don't have to use the whole language to write Haskell programs and to be productive with the language, right? Um, so less is more, I guess, a lot of the time. It's called C++, yeah. The reason why I don't like that comparison, by the way, is just because, like, if you look at the specification for Haskell 2010, if you look at the PDF of that spec, it's like 300 some odd pages, say like 350 pages. And I think even if you took modern Haskell as it's written today in a lot of large applications that have a lot of language extensions added, it still would be a fairly small specification relative to C++. The working spec for C++ 23 right now is still in working draft, and it's over 2,300 pages for comparison. It's a much, much, much bigger language by far. And when you start a C++ project and you work on a big C++ project, almost the first thing a style guide will do is like say, okay, we're using this part of the language just so that we can keep the code base kind of consistent and going in the same direction. We don't have to have debates about whether to use this or that or this feature or that feature, that kind of thing, right? Haskell on large code bases can have some of these debates where you might use other things like higher kinded data types or you know, kind constraints and I don't know, type families and other features to implement your programs, right? And these could be considered complicated features on the maker code complicated. So the philosophy of simple Haskell is like use as little as you can get away with. Or I guess is taking even more opinionated stand and saying you only need to use these things. And some of these features in Haskell are not good to use. Which I'm not totally on board with. But I think your point about applicative, use applicative if you can get away with it, is a good point, right? That's ties into this. What I think is interesting, my take on this is that like we should use like the sufficient level of features, the sufficient language features we need in order to express our problem on the various dimensions that we're concerned about when we're engineering software and we're developing software, right? We might be very, very much concerned with correctness, or we might have a lot of junior engineers on our team and we want to provide them a good developer experience where they're using the library properly and they have guardrails that are given to them at type checking time rather than at runtime or various other things. And Haskell has features for us to write libraries to do that, right? But if you can get away with just using applicative, monad is a very much stronger type class that has a lot more functionality to it, right? That might not be necessary, and you might make your code more complicated by using a monad when you can just get away with an applicative. And so sufficient is like invokes this kind of idea of necessity and enoughness, you know, without being like this is good or this is bad or this is simple or this is complicated. And it's kind of got a little bit of wiggle room to it, which I like. But yeah, sorry, that was a bit of a digression, but it's something that comes up a fair bit in Haskell circles. And I think that, yeah, using applicative where you can get away with it is a cool idea. And so it's a very cool solution, Countor, and thanks for sharing. And I think that's kind of what we're doing in this arcade game too. We're not using a whole lot of stuff that we could be in Haskell. Right? This is very, very constrained set of features we're using here right now, for now. But it becomes obvious later on as your program gets more complicated and does more things where you do need to use those more advanced features, more advanced type classes, more advanced language features, so on and so forth. It's always good to remember the basics. Yeah, we'll use flat map on list, or you could use map. Yeah, exactly. But isn't going for monad too frequently make it closer to C++? Well, I guess too frequently is a matter of taste. Like there's all these kinds of things that are going on in your program that you know about, right? That you as a developer might say, well, yes, it's sufficient to use an applicative here. We don't need bind, for example. But you might need it, right? And it's kind of like, well, then you use it, right? It turns out, I think a lot in programming, a lot of things are very monadic. C++ is getting monads, by the way. I think there's at least one data structure in the base library that's going to be like some kind of option type with like a monadic interface. One of my favorite ranges, yeah. One of my favorite people to follow in the tech sphere in Cybrand. They're super cool, and yeah, they've introduced that proposal to do that. So let's get this test case done before we run out of time on the stream. Yes, they're bringing a version of type constraints as well into templates, which they're calling it concepts, which is a very not good word, I don't think, but I don't think it's a very good word to say, but concepts, yeah, which is a super necessary thing for templates. Like, yeah, it's not a good word, but it's such an abstract thing that like, what are you gonna do? Haskell is kind of guilty of this, but the abstract names it tends to pick are ones where like there is a definition for it. It's given by laws and things like that. I've said the same things about like functor and monad back in the past when I wasn't familiar with these concepts before. But that's the other reason why I like the idea of like sufficient Haskell over simple Haskell. Is that sufficiency lets you have that wiggle room and I think that's important because simplicity is sometimes mistaken for familiarity, depending on who's speaking and who's saying what, who's defining what simple is, right? And it was, I think I might be mistaken here, but I think it was um, Dijkstra who said that, like, and I'm paraphrasing here, um, simplicity is a good virtue, but it's hard to achieve and often takes education to appreciate. And worse, complexity sells better. Right? But what I think he was talking about there, simplicity, is that it takes education to appreciate, is that things like monads and applicatives can make code much more simple because it has defined laws that you can depend on. And so once you are familiar with those laws and you're familiar with the abstraction, you can elide the underlying details and just work in the abstraction and not have to worry about it. Because the abstraction is strong, it has those laws that kind of back you up, so you can lean on those things. And that can make code simple in a manner of speaking. But it does take education to learn what an applicative is and how it works and what those laws are and what they mean. But once they're there, there's lots of things that are applicatives. There's lots of things that can be expressed as monads, for example. And so I find in my career it has really benefited me learning those things because it's useful outside of just Haskell. We can see these patterns, you can use them, that sort of thing. I don't know if you agree. Maybe that's complete BS, but all right, thank you, Countorn. You agree. All right, Stream fam, going strong. Okay, let's set up the A's list as well. Right, and we wanted this to be all C's, C, C, and C. Change that to asteroid. Oh, sorry, not CA. Okay, so we want 2 bullets to collide and 2 asteroids to collide. So that will definitely collide, as long as the hitboxes are set right, so. Which, yeah, the hitboxes are defined by the instance of the collision box class, so the asteroid is a fairly big one, so these should collide, yeah. So we just have to set the positions. So Countorin was solving having to go from your phone using Nix on Druid. Huh. Is that why you've elided all your type annotations and such? That's interesting. So do you run Nix on your phone? Not familiar with this. That seems wild to me, by the way. Wow. How does your phone not, like, instantly run out of space? Or does it have, like, garbage collection and all that stuff built in, so it does it automatically every time? But this asteroid we're going to make go out of bounds, like, completely far away, so it doesn't collide with anything. Okay, and then our expected A's list look like this, except we'll have that flag on a couple of them. Asteroid is dead. It's true. Wow, GHC compiler and Vim, no problem. Neat. Nix on Druid. Well, I don't have an Android phone, but that is super cool. Or is it Nix on Droid? Is it Druid? Mix Android. I think that's probably it. Oh, cool, cool. Cool, 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 cool. Right on. Neat. Wow, that's pretty cool. I've been thinking about, like I have a Steam Deck and I've been thinking about putting a development environment on it just so that when I'm on the go, you know, I can just put in a tiny little Steam Deck package instead of a whole laptop and just kind of plug in anywhere on the fly. It'd be neat to be able to bring. Yeah, I should look into that. Anyways, that's cool. Nix Android. Yeah, 3 kids is a lot, and I understand the time sink. I've raised 2. They're pretty big now, so I get some programming time to myself. But due to the fact that you have 3, and the only time you have is in between splitting fights up or picking up the baby, and yeah. No, that's important, right? You gotta be able to get those ideas down, and having like a little sketch pad where you can just jot down a little code is totally handy. Okay, yeah, my type error here. Ah, yes, is that these are lists, and we want them to be decks. I'll just add that. Okay, and we should be able to run our test now. Okay, we do have a failure. Cool. So we expected 2. Well, we got 14. Yeah, it really is it? Hmm. I mean, yeah, I could see that. I find it's not like it is like obviously you see me on the stream working on Haskell, you can see that I can get like type feedback pretty well. I can see some of the type errors kind of getting a little bit big for a phone screen. Yeah, that probably could be solved though. Okay, so good thing we wrote this test because we're not quite getting what we're expecting here. 2 versus 14. Let's just make sure we're kind of understanding our example here. Our bullet position at 0.5, not 0.5, and 1.5, 1.5. These are the 2 bullets we want to collide. I think probably what's happening actually is the hitbox for these asteroids are overlapping. And so this test is actually revealing an edge case for us, accidentally. Because we haven't quite done this yet. Which is good, actually. All right, so I think the reason why we're getting 14 here is because of that. This should be false still. Okay, and we're getting some maybe some things not in the right order that we thought they should be in. Mm-hmm. Right, because we're consing things back up when we're building we're doing this kind of sweep past thing. So since we're consing things on to the front of the list, these expected lists should be reversed. Now the order, I don't think really matters here so much. So we should just reverse these lists. Boop, boop, boop. Let's move you up to the first position. You down there. And you. And then the second thing that's happening is, yeah, the counts. So I think that we're getting more checks than we're expecting. More higher collision number than we're expecting because it's overlapping. Now, does 14 make sense for this case? Why could we get 14? I think we're running low on time, so we might have to leave ourselves with a failing test. Which is probably a good thing, a good little productivity hack, by the way. If it's getting to the end of your work day and you're not quite done what you're working on, don't leave yourself a failing test case. It's a great way to pick up a thread to work on in the next day to rebuild the context in your mind and of what you were working on and kind of get started again and have somewhere to go. In this case now, though, let's see. We expected the 2020 bullet to be first position. Should be. Oh, but we got, sorry. Maybe the order was fine. Yeah, you'll solve it right away. Just how it goes. Yeah, okay. So I don't... Let me reverse this here. That was fine. Yeah, asteroid is dead. Okay. I think what we're getting... So 4, I think 14. 14 might be because... how does 14 make sense? For each bullet, I've got to look through 3 asteroids, right? So 3, 3, and 3. That would be 9. Oh, right, and I think, in our algorithm there, we were adding together the found collisions from when we did the sleep for each bullet. So that I would still kind of expect that to be 333, even if all the collisions were happening here. Oh, sure. We're gonna have to wrap this up, but I'm just gonna try a couple of things first. We'll go fast and file watch. And we'll just mess around with a couple of these values to see if we can get just my theory here. So I think if we move this asteroid position like way far away, so it couldn't possibly collide with anything else. That's not going to affect anything. So I moved from list here. We should still see 14. Right, we do. Yeah, we got 14. So if we move this one out to 100, that should stop colliding with the other two bullets. Still getting 14 though. No matter what we do, we are getting 14 collisions reported. Okay, so it has nothing to do with the positions, it looks like. Oh, sorry, that's my expected. I'm manipulating the wrong thing. I'm a dummy dumb. Oh, dummy dumb, dumb dumb. That should affect it. Nope, still 14. It doesn't affect it. Okay. This one should be affected though. Let's make this one something super high. Okay. 7. Now we're getting 7 collisions. If I make this something ridiculous, we should get no collisions. Zero. Okay. So we're getting 7 collisions per bullet when it collides with detects an asteroid collision. It could also be the bullets are too close together, so that we're... Why does 7 make sense in this funky case? I think I have some ideas, but we're going to have to solve it another day because I'm going way over time here. So I'm saying it a lot. I'm going to call it. Thanks for tuning in to the stream. If this is your first time popping by, hi, I'm Agent Ultra, James. And you can follow me on the GitHubs where this code lives. And if you want to check out this code, you can. It's at Agent Ultra. It's Asteroids. Right here. So star, fork, whatever you want. It's cool. Just follow along. It's all good, but this is where it is. I do these streams once a week on Tuesday evenings at around 10 after 8 in the Eastern time zone. You can follow me on other socials at like types.pl /Agent Ultra. That's where I'm on the Masters Johns in the federated universe of stuff. You can, of course, go to the link above me here, declarative.tv. That's a cool site where a lot of other people who are doing things in functional programming and in other languages are streaming cool projects as well. So if you want more of that, go there. You'll find also a Discord link where we have a channel for this stream here, and you can join me in between streams to talk about your projects, to share your feedback, anything you didn't want to discuss on stream. Or maybe if you missed on stream, you're watching because you're watching on YouTube, you can find us there. So that being said, smash that button, like button, ring the bell, follow here on the Twitches, all that sort of stuff to get notifications when I go. Sometimes I do surprise streams off my normal schedule, so you can find out about those. And that's all I got for you this week. So thanks for tuning in. Again, may all your monads be free. May your types always check. Happy hacking out there. Take care.